Okay, so these are all synonyms. So the Calvin cycle, the carbon fixation, the Calvin-Benson cycle, light-dependent reaction, those are all talking about the same thing. They're all talking about the light-independent reaction, which happens without the help of light, and it occurs in the stroma, okay? So anytime you hear any of those terms, we're talking about the same thing. Calvin is the last name of the guy who discovered it, and then Benson also contributed, so they kind of share credit in that. So that's why you might see it called that. And then carbon fixation, it's where we're fixing carbon molecules to each other and then breaking them apart and then fixing them to other molecules. And so that's why we call it carbon fixation, because we're building bonds and breaking them. Okay, so this is where it starts. Okay, starting point is here. All right. So to start off, we have to have 3. So you have to fill this in, guys. 3 CO2 molecules. This is going to happen twice. So eventually we'll use 6 carbon dioxide molecules, but at first we just use 3. Okay. I drew the 3 CO2s right here. All of the carbons that I've drawn on this paper are empty circles, so go ahead and draw that over here. The empty circles are carbons, the filled in circles are oxygens, and then the PIs are phosphates. And then you guys already know that H pluses are hydrogen ions. Everybody got it?
Wait, what?
PI means phosphate. We haven't gotten to that yet. That's later on in the picture.
Okay.
Okay, so to start off the process, we have to have 3 carbon dioxide molecules in the stroma so that we can go ahead and start this thing off, all right? So 3 carbon dioxides are going to bond to 3 molecules called RUBP molecules. RUBP molecules, how many carbons do you count in each of those RUBP molecules? There's 5 in each of them, right? So you got to write that in there. RUBP has 5 carbons. Okay, so RUBP is a 5-carbon sugar, and there are going to be 3 of them waiting in the stroma that are going to bond to, each of them bonds to one of these carbon dioxide molecules. Okay, the molecule that helps that to happen is called Rubisco. That's already written up here. So Rubisco binds 3 carbon dioxide molecules to 3 RUBP molecules, and this is what we come out with. So y'all see the little kind of cloud thought that I wrote up at the top here? Rubisco binds CO2 to RUBP, and this is what the molecule is going to come out looking like at the end. Y'all see that? Okay? All right, so that's going to happen to all 3 of them. So now we have a 6-carbon sugar, right? Because we added a carbon with the carbon dioxide. Well, now we can move on to the next step. So kind of follow this arrow and move on to the next step. So here we have 3 6-carbon, you got to fill that in, 3 6-carbon sugars. I didn't draw the oxygens on here because it just complicates the picture. If it confuses you, you can add the oxygens. Y'all see how we have 3 6-carbon sugars now? Okay. All right. I didn't draw the oxygens, but it's actually just this same molecule. I just didn't draw them. Okay. What's going to happen here in the next stage is that those 3 6-carbon molecules that we just formed are each going to split down the middle to form 2 3-carbon molecules. So each of those is going to split down the middle. Okay.
Wait, for the last step before it splits, where's the
Oxygens?
yeah?
I just didn't draw them on there. You can add them if you want to.
They're just like
Yeah, but they are technically like here. If you look at the board.
yeah. And then so when it splits, where would they be? On one side or like one on each side?
It's good. They're just going to be on one side.
Okay.
Okay. All right. So then we are going to take the, okay, so we made 6 3-carbon sugars. So what's going to happen here is you see the six 3-carbon sugars that we made here? Y'all see it on this next stage? Okay. So those are called PGAs. It's gonna be easier for y'all to write this in here because y'all's marker isn't massive. So these are each called a PGA. So we have 6 PGA molecules here. A PGA molecule is a 3-carbon molecule. Y'all see that? Okay. All right, so now we can move on to the next stage here. So what's going to happen is that a phosphate is going to be added to each of these PGA molecules. So y'all read this little blurb down here. 6 ATP drop off one of their phosphates. Each phosphate dropped off attaches to one of the PGAs. Okay, so ATP is going to come over. 6 ATPs are going to come over. Each of them is going to give one of their phosphates to one of the PGAs. And then we're left with 6 ADP molecules. Y'all see that? Okay, so there's a little blank you have to fill in there. So we came in with 6 ATP. Each of them lost one of their phosphates, so now they are 6 ADP when they leave, right?
So wait, what?
Okay, so we've got 6 PGA molecules here. You got that part? Okay. All right, so then what we have 6 ATP molecules that come, and they add a phosphate to each of them gives a phosphate away. You see? And so when they leave, they are now ADP molecules. Good.
Okay.
All right, so coming down here so that we understand that, adenosine triphosphate is adenosine triphosphate. Oh, I lost my pen. Hold on a second. I accidentally put a screen over it. Okay. Adenosine triphosphate is how many phosphates attached to an adenine? Okay. Adenosine diphosphate is how many phosphates attached to an adenine? Okay. So when the 6 ATP molecules come in, each drop off one of their phosphates to attach to one of the PGAs, they're going to then leave as ADP molecules. Okay?
Oh, so that's what the
You got it?
Yeah.
Okay. All right. So now we're going to move on to this next step here. So the next thing that happens is that, and this got cut off a little bit. This is supposed to say NADP. Okay. So NADP, remember NADP and how it was carrying around hydrogens? Okay. From the light-dependent reaction. So NADP are going to come and drop off their hydrogens to be bound to the PGAs. Okay, so 6 NADPHs are going to come in and drop off their hydrogens to be attached to the PGA molecules. Since they dropped off their hydrogens, they're going to leave as NADPs. And they're going to go pick up more hydrogens from the light-dependent reaction. Okay? So now, the next part you're going to want to look up at is right here. Okay?
So it leaves as a what?
So the NADPHs come and they drop off their hydrogens.
So then it's just NADP.
Yep. Okay, so now we've got PGAs that have a phosphate bonded to one end because they got that from, what'd they get that from? What'd they get their phosphates from? Good, and then they have a hydrogen on the other end, or not necessarily on the other end, that's just the way I drew it to make it good visually, but they have a hydrogen attached. Where'd they get that from? Good. You got to write a 6 here. We got 6 PGALs, okay? So PGA, when it has a hydrogen attached and a phosphate, we now call it PGAL. It has a new name, okay? So now we have 6 PGALs.
Hold on one second.
Okay.
The L is the phosphate and the hydrogen.
Yeah, so adding that L stands for the fact that it has a hydrogen and a phosphate attached now. If that's the best way for you to remember it. Okay, so in this little cloud right here, next to this step, we need to fill in some blanks. So a PGal is a PGA with a what and a what attached to it? A hydrogen and a phosphate. Okay, so fill that in. Okay, then we're going to move on to this next step here. This is really the last step. Okay, so from here, one of the P-gals is used. Okay, so ATP gives the energy for 5 of the remaining P-gals to form RUBP. One of the P-gals leaves. Okay, so next to this arrow where things are leaving, you say 1 P-gal. Because 1 P-gal leaves. Which means that we're left with 5 P-gals. Remember that P-gals are 3 carbon molecule with a phosphate and a hydrogen attached. And they're not necessarily attached like this. The molecule is more complex than this, but this is just the way we're drawing it for simplicity's sake. So we have 5 of these left. And those 5 P-gals, how many sugars are there? If we have 5 3-carbon sugars, then how many carbons do we have? 15, right? 5 times 3. Okay, so we need to recycle these. These can't be used to form glucose. We need to recycle them. So what we're going to do is we're going to use ATP molecules to rearrange these to make RUBP again. Because since we have 15 carbons here, we can mix these around to make 3 5-carbon sugars, right? You understand that? Okay, so ATP comes in, and we don't have to go through the process of how this happens, but ATP gives the energy for these remaining 5 P-gal molecules that are left over that are not going to be used to make glucose to be rearranged to make RUBP again, so we can kind of recycle them. And now the cycle can happen again. Okay? All right, so let me start back from the beginning, and then we'll kind of put everything together. So we got the Calvin cycle, okay, also known as carbon fixation, also known as the Calvin-Benson cycle, also known as the light-independent reaction because light is not required for this part. What happened right before this, though? The light-dependent reaction. What are we using from the light-dependent reaction? NADPH and ATP that was made at ATP synthase. Good job, Patrick. So 3 CO2s are going to come in. Rubisco is a molecule that's going to help those CO2s bond to the RUBP molecules that are waiting here in the stroma. So 3 CO2s bond to 3 RUBPs. Okay, the CO2 has 1 carbon, the RUBPs each have 5 carbons. So now we've made 3 6-carbon sugars. Okay, those 3 6-carbon molecules are going to split straight down the middle, making 6 3-carbon molecules. Each of those is called a PGA molecule. Okay, next, hey guys, can one of y'all close the door, please? Thank you. All right, so we've made 6 PGA molecules. So now what's going to happen next is that 6 ATP molecules are going to come in. Each of them is going to give one of their phosphates to one of the PGA molecules, okay, which means the ATP now becomes ADP. So 6 ADPs have now been released. And each of the PGAs now has a phosphate on it, okay? Next, NADPH is going to come and drop off its hydrogen. So we have 6 NADPHs that come. They each drop off a hydrogen to attach to one of the PGAs. Now the PGAs have a phosphate attached to one end and a hydrogen attached to the other end. Each of the 6 of them have a phosphate on one end and a hydrogen on the other end. Okay? Now that we have that, those are called P-gals. A PGA with a hydrogen attached and a phosphate attached is called a P-gal. One of those P-gals is going to be used to make to make glucose, and the other 5 of them are going to be rearranged using ATP to make RUBP again, so that we can go through the process again. Okay? The process happens one more time. Okay, so when the process happens once, we get to keep 1 pGal. Okay, we get to keep 1 of these. What about the second round? We get to keep 1 again, right? So when we come back through one more time, we get another 1. So now, after we've gone through the process twice, we now have 2 pGals. We've used 6 carbon dioxides, and we can make 1 glucose molecule.
2 or 3?
Well, each of these has, how many carbons does glucose have? Yep, so we just need 2 pGals, because each of the pGals has 3 carbons. Okay?
It has to go around twice.
Uh-huh. Yeah. Which the common question would be, well, why don't we just use 2 of the pGals, right? But their answer is that then we wouldn't be able to make more RUBP. Make sense? We have to always have enough carbon left over to make RUBP again. Yes?
Where is some ATP